I'll finish off the last theorem for this chapter, which theorem 63, and then combine that in the same session with three questions in the problem solving. I think there were 6 questions at the back of chapter 18. So do my usual half, more or less. Okay. Right. So theorem 63. You've got a mapping between groups G and H. The usual. F is a homomorphism, which I'm now shortening to just homom, right? Homom dot. Okay. A bit of quick revision on the nature of a kernel. What is a kernel? It's a subset of G, and every member of that subset maps to the unit of H, right? So B of H, the unit of H. And you can prove all kinds of properties about the kernel, that it's not just a subset, it's a subgroup, it's a normal subgroup, and so forth. And here's another property about the kernel. It just gets richer and richer, right? So here's you may remember at the bottom here in the previous session, I posed a question: if x and y, if I can remember correctly, perhaps I better prompt myself from the book. Oh yeah, if x and y map to the same element in H, so in other words, f of x equals f of y. What can you say about x and y if they map to the same element in H? Well, here's your answer. So if they map to the same element in group H, then well, here's your statement. So f of x equals f of y if and only if these two elements in G, x and y and G, belong to the same coset of the kernel in G. Right? Now, kernel, from previous session, we know is a normal subgroup of G. Right? So think of this as N, a normal subgroup from earlier theory. Right? So you're probably used to, one of the theorems earlier, we wrote it in the form of the coset A is equal to X capital N, right? But now we're talking about the kernel, which is a normal subgroup, and we're writing it. We're writing this in shorthand as just capital K for the kernel. Right? So the kernel of F now we'll just write as capital K for shorthand. All right. So the X and Y just members of G, and if they map to the same point in H, if this is true, then X and Y belong to the same coset of kernel F. In other words, this normal subgroup. Right? Okay. Now it's an if and only if. So as usual, start with the if side. That means we go from right to left. So we start with these two belonging to the same coset of this normal subgroup of Ker F, and we have to prove that these two are equal. Right? Okay, so we'll start with this. So we're given this. So X and Y belong to the same coset of K. All right. Now, again, we're using theorem 46. Incredibly useful theorem, especially for this kind of work. Right now, a reminder: the second part of theorem 46 says what? It says that well, it's an if and only if, but only use part of it. So if x belongs to some coset A, right, then A equals x. Well, a normal subgroup that you were talking about, a coset of some subgroup. Which one? Well, in this context, we're talking about kernels. So the normal subgroup here, instead of being just n, it's k. It's a specific subgroup, normal subgroup k. We're talking about kernels, right? So if x belongs to some coset k, if you like, then A equals xk, right? Now, we're assuming that x and y belong to the same coset. So y belongs to the same coset. I mean I'll just make it k, right? Better be careful. This can be some other coset besides k. Alright, so if x belongs to coset A, then we have this. If y belongs to coset A, so in other words x and y belong to the same coset, A equals yk. Well, A equals xk and A equals yk, therefore xk equals yk. Right? Now, from the first part of 46, this was from the second part, this is from the first part. If you have this, so if xk equals yk, so xk equals yk if and only if x inverse y belongs to your normal subgroup, your in this case bk, right? Now I've written down here on the side here, if x inverse y belongs to your kernel bk, then that means that x inverse y must be equal to some little k here, that belongs to your kernel, right? That's just sort of common sense, right? So we can rewrite x inverse y equals little k here. All right, now we're trying to prove this. Right? We're given these two belong to the same coset of your kernel, and we're trying to prove f of x equals f of y. So you may ask where this came from. Well, the answer is we're trying to show that that equals that. Now, if that's true, this will be true. This is just rewriting this. How do I get this? Well, multiply on the left-hand side of both sides by the inverse of f of x. Right? So if I do that, I'll get the inverse of f of x times f of x. That's just e of h. Right? They just cancel. And here I'll get the inverse of f of x. That's this times fy. Right? So that there must be equal to e of h. Now, why am I doing that? Well, I'm trying to prove this, and if that's true, then this is true. So let's try and prove that this is true. Well, prove that this is true. And if that's true, then that's true. That's the strategy. That's the proof strategy. Right? Well, what is this? So now we're trying to show that this is equal to e of h. And if that's true, that's true. All right. So let's rewrite this. So you've got it here again. Now, one of the earlier theorems we did, just previous session, was, well, anyway, recent theorems that inverses in a homomorphism map to inverses. So the inverse in G will map to the corresponding inverse in H. Okay? So the inverse of f of x is equal to the f of inverse. So that was one of the theorems, part of one of the theorems we did fairly recently. Okay? So the inverse of f of x is equal to the f of inverse. So we can rewrite that as this, right? And since f is a homomorphism, so f of m times f of n becomes f of mn, that kind of thing. So we can rewrite this as this, all right? Now, here's our old friend, x inverse y is little k. Here, x inverse y is little k. Little k is just some member of the kernel, big K, right? So I can rewrite this as just little k. Now, f of little k, what's that equal to? Well, it'll be the unit of h, right? So, I mean, what is little k? It's a member of the kernel. And what's a kernel? A kernel is the set of all the elements that map to e of h. So if little k is a member, if it belongs to this kernel, big K here, it will map to e of h, right? So f of some member of the kernel, little k, will map to e of h. And there we've got it. So this equals this, which is what's said here. Now if that's true, that's true. And we've proved it. At least for the if part, going from right to left, we've proved it. All right, now going the other way. So now we assume this, we assume the left-hand side, and we have to prove that x and y belong to the same coset of your kernel. All right. Again, just shorthand. Use capital K for your kernel. So think of this as similar to what we did before, as capital N, like your normal subgroup. All right. And we're given this. We're given the left-hand side. So f of x equals f of y. Now, you may ask, well, where did this come from? Well, it works. Proof strategy. It's often the way you're looking at a proof. I don't know about you, but I find often reading other people's proofs, especially if they're written by genii, trying to understand their proofs is a continuous IQ test. I suppose a lot of you feel like that. All right. So try this, and you'll see by the results that it was worthwhile. So let's try to find f of x inverse y. Now f is a homomorphic function, so you can split this up into this form, right? That's just your f of mn thing again. So this is true here. Now inverses map, it's a homomorphic mapping, f. So the inverse of your g maps to the inverse of your h. Right? So this is equal to this. Right? We had the same phenomenon here and here. Right? It's just the same thing. So we can rewrite that